Welcome to Mancinelli's Math Lab. Thank you for joining me once again. I wanted to create a follow-up video. I'm going to link up here in the upper right corner the video I created through Excel, which was discussing, God, I need to stop saying frequency, severity, pure premium trends. A lot of people asked, what do we do with those? Well, you'll see in a video coming up, but right now I wanted to just show you actually the derivation specifically of the fitted value B. If you recall, the fitted value B is what actuaries typically use to determine frequency, severity, pure premium trends, also pure premium trends themselves. So we use the exponential fit, specifically that growth, that B, that exponent of the exponential E, which is really just the base of an exponential if you think about it. If you determine, let me write some stuff down. So we're looking at y equals a e to the bx. And if you think about this for a second, just to digress a moment, this is the same thing as saying this was equal to a and then e to the b raised to the x, right? Because if you recall from high school algebra, if you take an exponent to an exponent, you multiply the exponent. So e to the b to the x is e to the bx. And what I'm getting at here and why I'm focusing on this for a couple of reasons, because this value B is really what we use for severity trend, for frequency trend, pure premium trend, and also premium trend. So it comes up a lot in the day-to-day work as an actuary. So I was very curious for a long time, what's really going on there mathematically. So I'm going to show you right now. So read the question 5 to 100 times. I have it up here on my computer as well. So what we want to do is we want to essentially find the fitted exponential curve. And so if you've studied in a statistics class or for one of these actuarial exams, general linear models, specifically generalized linear models, that's pretty much the topic that this falls under. Well, not pretty much, but that is the topic this falls under. So in the question, notice I specifically want to find what B is, again, because that's what we're interested in. That's the value that's used a lot. So I want to just go over the derivation of that. You can find A as well, but it's just a lot of messy algebra. I mean, let's be honest, algebra is not that interesting. Manipulating equations is not that interesting. So I just want to give you a rundown of how we get the B value, because that's what's important. So let's write this a different way. So here's my exponential function. And well, we're going to have to take some derivatives, so let me write it another way. So we want to find B, and typically this is given with a little hat over it to distinguish it from the actual B in this exponential curve here. The fitted value B, such that the predicted value y hat I is equal to a hat e raised to the b hat xi. Now, why did I put these i's as subscripts? The reason is when you're actually doing this, you are fitting a curve to some data. You're given a bunch of values. You're given a bunch of ordered pairs, xi, maybe x1, y1, dot, 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 all the way down to xn, yn. So maybe we're given a bunch of data points and we perform some sort of goodness of fit test, maybe like r squared, and we determine that the exponential curve fits this data well. So I want to find specifically a hat, b hat, such that it fits this data well. This is why the i's under as subscripts for the yi and the xi. So the question tells me to minimize the sum of squares error. Again, ignore my dog snoring. Always the situation. So let's take the ln of this, okay? So this is the same thing as saying that we have ln of yi is equal to ln of a hat plus b hat xi. So this is really a generalized linear model, and the reason is because this is the log link. So this whole thing, this whole equation, this whole function is a generalized linear model. So what we want to do is we want to minimize the sum of squares error. And if you just think about this intuitively, I think it makes a lot of sense. So what we need to do is we need to minimize the sum of squares error. What is the sum of squares error? The sum of squares error is equal to aka the residual sum of squares is equal to what happens when I sum up all of my response variables, my y's. These are really my observed values, right? My yi's, and then I subtract off the predicted value squared. If you think about this for a second, what are we really doing? We're really minimizing the distance. This is a lot like a distance. In fact, this is a lot like the Pythagorean theorem, really. If you think about this, this is like the square root of the sum of differences squared. It's not like the Pythagorean theorem, it's not like the distance. So we're really minimizing the distance between our observed value and our predicted value. That's exactly what you want to do when you're fitting a curve to some data, right? You want the curve to be as close to each data point as possible. So we need to minimize this, and this is equivalently, we want to minimize this guy, the sum of ln of yi minus ln of yi hat quantity squared. And when I do it this way, basically it's a little more straightforward. Here we want to minimize this, the sum of ln of our response minus ln of our fitted value squared. And now I want to rewrite this. So therefore we need to solve, we're going to have to solve a system of equations. Let's think about this for a second. I'm going to have to solve what two equations? Whenever you want to minimize something, and think back to when you're in a calculus class, you want to minimize something, this is essentially an optimization problem. And when you're solving an optimization problem, you essentially want to find the derivatives, set them equal to 0, and then find, well, hopefully it's a maximum or minimum, so you usually have to do some kind of test to make sure that it is. But a lot of times these optimization problems, the only critical value you get is the min or max, and this time is no different, fortunately. This would technically be covered in a multivariable calculus class because it's functions of two variables. I need to find solutions to the following equations. I need to take the derivative, the partial derivative of this. If you recall, this ln of yi hat is equal to, so ln from the prior, ln of yi hat is equal to ln of a hat plus b hat xi. So I'm just going to make a substitution, and now what I'm looking for is I want the partial derivative with respect to a hat of this guy, so ln of yi, minus ln of a hat minus b hat xi squared equals 0. If you think about this, this should make sense to you, I hope, because we are looking for where is the derivative with respect to the parameter a hat equal to 0. We're solving an optimization problem. Remember, derivatives are 0 if you have like some sort of peak or some sort of trough. So hopefully we're some sort of trough, visually speaking. And we need to do the same thing with respect to b hat. So partial with respect to b hat of the same quantity, the sum of ln yi minus ln a hat minus b hat xi squared equals 0. So here are my two equations. My two unknowns are, you can either think of them as ln a hat, essentially ln a hat, and b hat. So let's go ahead and do that. And remember, specifically I'm interested in the value of b hat. I don't really care about a hat because it doesn't really pertain to what we're actually doing. I mean, I'm pretty much in the realm of applied math now, so let's just do what we care about, which is b hat. In order to do that, though, I need to find this guy first. If I take this derivative, something you should be thinking about is, first of all, this square is on the quantity inside the sum. So the summand, this is called the summand, is being squared. So if I want to differentiate this, do we need to worry about this summation out here? Well, this is a finite sum, so we don't have to do any weird mathematical theory to convince ourselves that we can do this, because it's a finite sum. You can always pass a derivative through a finite sum. So if I pass this derivative through, I'm going to have to apply the chain rule here because this whole thing is being quantity squared. So what I have from equation 1, let me just call this equation 1. These are two different equations. From equation 1, what I have, take that derivative with respect to a hat and I get the following. I get the sum. The 2 comes down, applying the chain rule. Leave the inside alone, ln of yi minus ln a hat minus b hat xi. So I brought the 2 down, leave the inside alone, times the derivative of the inside. The derivative of the inside with respect to a hat is negative 1 over a hat, and this all equals 0. Remember, the derivative of ln is 1 over the thing inside the ln, 1 over the argument. So this is what I have. Now, a hat is definitely not 0, so we can divide by a hat. If a hat's 0, then my exponential function is not an exponential function. It's a horizontal line at 0. So that would be silly. So why don't we just multiply both sides by a hat and get rid of that negative as well. So now this gives me the following. I have, we can distribute the sum as well. Actually, get rid of the 2, divide the 2 out. So I just have this business in here. This is equal to the sum ln yi minus, now if I sum ln of a hat, if I sum that, that's going to be n times ln a hat, right? And then minus b hat, the sum xi equals 0. What I want to do here is I want to solve for ln of a hat. So let's go ahead and do that. If I solve for ln of a hat, then I get the following, ln of a hat. Bring everything to the right-hand side and then divide by negative n. So what I get here is b hat xi, and then minus the sum ln yi, and then I need to divide by this negative n. So actually, let me do this. Let's make this negative and this positive and divide by n. So this is the value I want to use for ln of a hat. And remember, I'm really not that concerned with what a hat is, because as far as on the job, we are really interested in where does this b hat come from. This b hat is used all over the place. This is why I care about it. Otherwise, I wouldn't even be doing this. So let's give myself some more room. Now we can finally find b hat. For b hat, we're going to need this, so I kept it here. But what we're going to need to do, if you recall, is take the derivative with respect to our other parameter, b hat. So let me just write that down again. We're looking to solve the following, the partial with respect to b hat of the sum, and then I have my ln of yi minus ln of a hat minus b hat xi quantity squared equals 0. This is the equation I need to differentiate. I need to set it equal to 0, set the derivative equal to 0, right? Let's go ahead and do that. So again, we have to apply the chain rule. So on the left-hand side, I'm going to have to bring the 2 down. I'm going to make the sum, and then I have 2 times, leave the inside alone, applying the chain rule, minus ln a hat minus b hat xi. Now I've brought the 2 down, leave the inside alone, times the derivative of the inside with respect to b hat. This is times negative xi equals 0. If I differentiate with respect to b hat, then you treat xi as a constant. So this is what I get. Can we just divide by xi? Can I just get rid of the xi? No. For one, it depends on the index. I mean, if you wanted to be very thorough here, this would be something like I equals 1 to n. So xi depends on the index. You can't just divide it out. We could do it before because it's just a constant. Furthermore, xi could be 0. We can't divide by 0. So a couple of reasons why you can't get rid of it. Let's distribute it through. So what the following now becomes, I can't get rid of the 2, by the way, right? The 2's gone. By the way, the 2 does not matter. So now I have this. So now I have the sum and ln yi times xi. So I'm taking this xi, I've gotten rid of the negative, get rid of the negative, and distribute this through. Distribute this all the way in here. So now I have ln y xi minus, let's distribute the sum as well, because now this is going to be ln a hat times the sum of xi, and then minus b hat the sum xi squared. So let's see. This looks good. Equals 0. Now I need to make a substitution for what ln of a hat is. So now this gives me, same thing here, so sum ln yi xi minus, now what is ln a equal to? It's equal to this stuff, so let's throw that in there. So now I have, I'm just going to reverse the order. So I have the sum ln yi divided by n, and then minus b hat the sum xi divided by n. This is being multiplied by the sum, so this is multiplied by the sum of xi, and then I have minus b hat the sum xi squared equals 0. So we're getting there. We're almost there. Last thing I need to do is I need to get b hat by itself and divide by the rest. So keep everything with b hat on the left-hand side. Let's do that. All right, so it looks like I'm going to get a positive b hat right here. So let's write it this way. This is going to be positive b hat. This gets distributed. So I have this. I have the sum xi. Now this sum is squared, right? Sum xi times sum xi squared, all over n. Now I want to bring this guy in here. So this is going to be actually minus the sum xi. Now here the square is inside, just applied to the xi. What's on the right hand side? Well, let's bring this guy over. So this is going to be the sum ln yi over n. Okay. And let's bring this one over to the right hand side as well. So minus the sum ln yi xi. Let's see how we are doing. Well, I forgot a term, didn't I? I forgot this little piece. This needs to be multiplied in there as well. Oh, brother. That's all right. We can do that. So this is going to be, I just forgot this piece. This is the sum xi. I forgot to distribute that. Now I have this one, so minus the sum ln yi xi. Now I want to clean it up a little bit. I want to make it look like what I've written down here as what we're supposed to get. To get what we have in the question, multiply both sides by n, and then multiply both sides by -1. You can think of this different ways, but basically I'm going to switch this order, and I'm going to switch this order, and I'm also going to multiply by n. So what we should get when I do that is I should get that b hat is equal to what? This is going to be n times the sum ln yi xi minus the sum ln yi times the sum xi divided by n times the sum xi squared minus the sum xi quantity squared. And this is what we get. We're good to go. This is what I was looking for. And I just want to reiterate, I'll link some videos to this, but again, I use this in the Excel video to show you that this does exactly what the LOGEST function does in Excel. As an actuary, use the LOGEST function. We use Excel all the time. We use the LOGEST function to find this. If you want to do it by hand, which you never do, you would do this. But it's always good to know where things come from. Now you know what's going on. There's nothing more annoying than doing stuff without really understanding it. In my opinion, not fun, not cool.